Hi everyone, today a video in the transition metals and inorganic reactions set of videos looking at coloured ions. Now we've talked in a previous video of this series that one of the key properties of transition metal ions is that they tend to form coloured ions. And this is in contrast to a lot of main group ions or even organic compounds that tend to be white solids or colourless liquids. Now the colour of transition metal compounds is due to the compounds absorbing energy that corresponds to light in the visible region of the electromagnetic spectrum. And we'll see on the next slide that the reason for this ability to be able to absorb energy in that region comes from having the part-filled d orbitals, that really key property we've seen throughout this set of videos. The key fact is that these transition metal ions have part-filled d orbitals. The other key factor is that it's in the visible region of the electromagnetic spectrum. Other main group ions and organic compounds also absorb light and cause electronic transitions, but that light is not in the visible region of the electromagnetic spectrum, and therefore as humans we don't see it as colour. Now the colour of the compound that we see is all of the colours, and of course the colour is related to a wavelength of light and a frequency of light. The colour of the compound is all the colours that have not been absorbed. So we essentially see the colour that is remaining. And so we can see this example here in the middle. If I take some white light, and white light is a mixture, essentially a whole spectrum of colours. If I shine this through my solution, energy that corresponds to the colours there you can see from kind of green to red is absorbed by the compound. So those wavelengths of light, those specific colours are absorbed by the compound. Therefore, we see what's remaining, which is that kind of bluey colour at the end. So the solution appears blue to us because all of the other colours, the green, the orange, the yellow, the red, has been absorbed by the compound. So we see what is remaining. Now you can monitor what has been absorbed by something called UV-vis spectroscopy, which stands for ultraviolet and visible light spectroscopy. And all we're looking at in here is essentially what wavelengths of light are absorbed by our compound. And so the spectrum that you would get out is shown at the bottom. This has absorbance up on the y-axis, literally sort of how much of that light is absorbed by the compound. And then we have wavelengths along the x-axis. And so you can see that for this sort of example that we would see here where the solution appears this blue colour, you may get a UV-vis spectrum that looks something similar to this. You can see that we have a fairly high absorption here in the kind of green, yellow, red region, but nothing within that kind of blue region around sort of 400 to 500 nanometers in wavelength. There's no absorption there. There is absorption from sort of 550 onwards to 700. And so that's what we'd see for that compound above that appears blue. What we're seeing is that it absorbs all these colours, the kind of green to red. We see the colours that are then remaining, the colours that have not been absorbed by that compound, the wavelengths of light that have not been absorbed. Another example would be that if all of the wavelengths except red and blue were absorbed by the complex, so it absorbs the kind of yellow and the green and the purple, but we leave red and blue wavelengths, then only the red and blue colour would remain. And if you mix red and blue together, you get purple. So we would see a kind of purple coloured solution. So the key thing is that we see the colours that are remaining after all of the other colours have been absorbed by the compound. And the way that we can kind of work out what colour we expect to see and what colour, if we have a coloured solution, what colours must have been absorbed, is by using something called the chemistry colour wheel, which is shown there at the bottom. And you can see that it's a very standard colour wheel that you've probably seen before, just this time we have the wavelengths that correspond to these specific colours. So for example, violet is between 360 and 420 nanometers, orange between 590 and 630 nanometers, and so on. And essentially what we mean by saying that it absorbs some colours and we see what's remaining is, for example, let's say we absorb that kind of, take the example we've been looking at this slide, the kind of green through to red, so roughly kind of, let's say, almost kind of 580 through to 720, we absorb those colours. Basically what we do on the chemistry colour wheel is just go directly through, kind of go through the opposite colours. So imagine going 180 degrees from that kind of region, and you end up in the blue region of kind of 420 through to sort of 490. And so simply all you do, if you have a compound that has a certain colour, you look for that colour on the chemistry colour wheel and you go directly through sort of 180 degrees almost, if you like, and that will then give you the colour that that compound must have absorbed. Likewise, if you know what colour the absorption is, if you know from the UV-Vis spectrum which colours are absorbed, you'll be able to predict what the colour of the compound would be by again going through this kind of inversion of the chemistry colour wheel. And so, for example, if you have something that's absorbing in the red region, it's likely that the colour that you would end up seeing would be a kind of bluey-green colour. If you had something absorbing in this kind of purple-violet region, you'd expect the compound to kind of have a yellow or green colour. Now, as we said on the previous slide, the really key thing that allows these transition metal compounds to be coloured is because they have those part-filled d orbitals. Now, for any element, or if you have an isolated metal ion just on its own, these d orbitals all have the same energy. We've always talked about within electron configurations and things like that, that our d orbitals, our 5 d orbitals, have the same energy. However, when you put these metal atoms, these metal ions, in the presence of ligands, lots of other atoms and molecules, the d orbitals can actually split in energy. And so we get some that go up in energy and some that go down in energy with respect to where it started of those 5 of equal energy. Now, the exact splitting pattern depends on the shape of the complex. And you don't need to remember these splitting patterns for A level. It's just to give you a bit more information, hopefully, so you can understand where this all comes from. So when our complex absorbs light that is exactly equal in energy to the difference between the two split levels, this can promote an electron between the d orbitals. So our colour essentially comes from electronic transitions. Now, we've probably seen lots of other spectroscopic techniques in our A level before. If you think about infrared spectroscopy, we're looking really at vibrations within the molecule. If we think about NMR, we're looking at the spins of the nucleus. In UV-Vis spectroscopy, what we're really interested in is electronic transitions, literally electrons moving from one sort of energy level to another. And so when we have that exact amount of energy that is supplied between the difference in those levels, this can promote an electron between the d orbitals from the lower level to the higher level. And by absorbing that wavelength, that energy gap, it's absorbing the energy. The energy is related to the wavelength and the colour and the frequency of the light that we see. And so therefore, the colour that is related to this transition is missing from the spectrum. That's the colour that our compound absorbs. And therefore, we see the combination of colours that are remaining at the end. And so we can think about our 3d orbitals. Remember, you don't need to remember the shapes of the 3d orbitals for A level, but you can see they have these kind of quite complicated shapes. But essentially, you can split them up into 2 main groups. The first group at the top is the x, y, x, z, and y, z orbitals. Now, these are orbitals that have 4 lobes each, and they actually point in between each of these Cartesian axes. So you can see that we have our x, y, and z axes, and that the lobes of these orbitals actually lie in between all of these axes. So for the xz orbital, the lobes lie between the x and z axes. They never lie along the x and z axes, they lie in between them. The other set is the 2 at the bottom, so that's the x squared minus y squared and the z squared orbitals. Now you can see the z squared has that kind of slightly funny shape in that we've only really got 2 lobes and then this kind of donut shape in the middle. But our x squared minus y squared also has 4 lobes. The key thing here is that our lobes point along the axis directions. So the x squared minus y squared orbital lies along the x and y axis, not in between it, along the axes. And our z squared orbital lies along the z axis. So essentially you can split that into the 3 orbitals that lie between the axes and the 2 that lie on the axes. And this is really important because our energy splitting depends on the shape of the complex. And if you're interested in learning a bit more about this, this is something called crystal field theory. And essentially what we're going to consider is if we have either our octahedral or our tetrahedral shape here, if we consider bringing our electrons that are negatively charged into the positions that form that shape, we think about how they interact with the orbitals. And that's why it's important to consider the axes that the orbitals are on, because they will either then directly interact with electrons, or they will kind of be, in the case of some of them being in between axes, they won't interact directly with the electrons. So it's all to do with the shape and how the electrons interact with the axes for the shape and also with the orbitals. Now, for an octahedral system, what we find is that our ones that lie between the axes, the x, y, x, z, and y, z, actually go down in energy, while our x squared minus y squared and the z squared, the ones that lie along the axes, go up in energy. Now, the reason for this, again, you can look more into this in crystal field theory, and again, you don't have to know it for A level, but it's just when you think about the shape of an octahedron, that octahedral shape, we think about bringing essentially taking our metal ion and then bringing our ligands in to form that octahedron. the actual where the ligands lie in an octahedron is directly along the x, y, and z axes. And so what that means is if we think about bringing our ligands along in towards the metal along those axes, ligands we think of as having lone pairs, negatively charged, or at least negative electron cloud. And our orbitals from the metal atom probably contain electrons, negatively charged as well. So bringing these two negative things along the axes to meet each other is a very repulsive process. Therefore, things go up in energy. And then conversely, our orbitals that lie in between the axes, they don't feel as much repulsion because the ligands are being brought in along the axes, these orbitals lie in between them, and therefore there's less repulsion, and so these actually go slightly down in energy, they're slightly stabilized. And so you can therefore see that if we take this 3D8 configuration here, that we split this up so that we have our 6 electrons in the bottom, 3 orbitals, and those 2 unpaired electrons in the 2 orbitals that are at the top. And so this is our octahedral splitting. Another one that's useful to think about is tetrahedral. Now this essentially is just the other way round. So for a tetrahedral complex, if we think about where the actual ligands lie, if we think about a sort of tetrahedral shape in 3D and we think about where the ligands lie, they actually lie in between the x, y, and z axes. And so what that means is that the orbitals that lie in between the x, y, and z axes feel more repulsion from those ligands. They go up in energy, whereas the orbitals that are directly on the axes don't feel as much repulsion and so are slightly stabilized and go down. So in this case, you have your 3 that are in between the axes, the x, y, x, z, and y, z going up in energy, and the 2 that are in between the 2 that lie along the axes, going down, being stabilized. So the x squared minus y squared and the z squared goes down. And again, this then gives us, if we have a D8 configuration here, this 8 electrons in our d orbital, that we can have the 2 at the bottom, 2 filled orbitals, and then as we go up, we have 1 filled orbital and 2 singularly filled orbitals. And again, there'll be an energy gap between those 2 split states. Now again, I'll just reinforce that you don't have to know these splitting patterns, you don't really have to know anything about crystal field theory or the d orbitals. This is just to help you understand where this splitting actually comes from. And the degree of splitting depends on a number of factors, but the 2 key ones really are what central ion we have, what metal we have essentially, and the ligands that we have. Now the energy difference between these levels affects how much energy is absorbed. The bigger the splitting, the bigger the energy gap. The smaller the splitting, the smaller the energy gap. And so that depends on, that affects how much energy is absorbed when we promote our electron from the lower to the higher. And the amount of energy that governs the colour of light that we see has an equation. This equation is delta E equals h nu. So delta E is our energy gap between the lower and the higher states. H is Planck's constant, just a number. And then the symbol that looks like a V, it's called nu, is the frequency. Now, frequency and wavelength are inversely proportional to one another, and so you can also write the equation out using wavelength instead, which is that delta E equals hc over lambda. So delta E, again, that energy gap between the 2 states. H is Planck's constant, c is the speed of light, another constant, and then that symbol at the bottom there is our wavelength symbol, lambda. And so either one of these is correct. Delta E equals hv, or delta E equals hc over lambda. And so frequency is directly proportional to energy. A bigger frequency gives you a bigger energy. Wavelength is inversely proportional to energy, so a bigger wavelength gives you a smaller energy gap. And so this amount of energy, this energy gap, governs the colour of the light absorbed, because the amount of energy essentially relates to the frequency and the wavelength, and therefore the colour of light absorbed. Now, the colour is determined by that energy gap. That's what determines whether our colour is blue or green or red. It's all to do with how much splitting we get between those levels. Now this depends, as I said, on the central ion. It depends on the oxidation state of that central ion. It depends on the charge of the complex. It depends on what ligands we have, the shape of the complex, and hence the coordination number. Remember that the coordination number is the number of coordinate bonds. And so different compounds of the same metal can have very, very different colours. We'll see this in the last video of this series, that we can take a particular metal ion, and depending on the ligands that we have and the shape of the complex, we can get very, very different colours. The key thing, though, are that it is the part-filled d orbitals that are the factor. We have these part-filled d orbitals. If they were full, or they didn't have any electrons in at all, once these orbitals split in energy, when they come into contact with the ligands, there wouldn't be any electrons to promote, and therefore no energy would be absorbed. So, for example, the scandium 3+ ion, where we take our scandium having sort of a 4s2 3d1 configuration, we think about doing the 3+ ion. that becomes essentially just 4s0, 3d0, so no part filled d orbitals, so that's colourless. Also, the scandium plus 1 ion is also colourless because that would just be 4s2, 3d0. And so again, we have empty d orbitals. It also goes true for zinc as well. If we think about the zinc 2 plus ion, zinc 2 plus has an electron configuration of just 3d10. Remember, we lose our 4s electrons first, so zinc is 4s2, 3d10. Remove the 4s electrons, we're just left with 3d10, and so zinc 2 plus is also a colourless ion because we don't have those part-filled d orbitals. So we have to have part-filled d orbitals. That explains why transition metals are coloured and why lots of main group and organic compounds aren't. And also that energy gap between the two states is in the visible region of the electromagnetic spectrum. It corresponds to visible light, and so therefore we see it as colour as humans. Now the final thing to talk about is something called colorimetry. Now colorimetry can be used to help us find the ratio of metal ions to ligand in a complex. And so if we have the ratio of the metal ions to the ligands, that can help in giving us the formula of the complex. And so a colorimeter essentially measures the absorbance of a particular colour. And so the way that we do this kind of experiment is we take one solution that contains the metal that we're interested in, another that contains the ligand. So the example we're going to look on this side is where we have a complex which contains an iron atom and something called a thiocyanate ligand, SCN-. Now this has a very strong blood red colour, this complex. But if we weren't sure of what the actual formula of the complex was, essentially how many water ligands were attached, how many thiocyanate ligands were attached, we could use colorimetry to help us determine that. So we'd have one solution that contains the iron, essentially the metal that we're using, so probably a hexaaqua iron atom, or an iron complex ion, and the other would contain the ligand that we're interested in this case, the thiocyanate solution. So we'd have an aqueous, probably potassium thiocyanate solution. Now these two solutions are mixed together in different proportions. And so you can see the graph at the sort of the bottom right here. You can see that as you go along the x-axis, you're mixing these two different solutions in different relative concentrations. So we go from having 5:1 for the iron to the thiocyanate, so a much higher excess of the iron than the thiocyanate. And you can see as we go from left to right that we increase this thiocyanate concentration relative to the iron to the point where we end up having 5 and 5, so a 1:1 ratio, all the way through to having 5:10, so that's double the amount of thiocyanate than we have iron. Now when our metal and our ligands are mixed in the same ratio as they actually exist in the complex, remember that we don't know what the formula is at this point, when they're mixed in the same ratio as the complex, what we see is a point of maximum absorbance on this graph. And so when they're mixed in the same ratio of the complex, what this means is that we have the maximum concentration of the actual complex in the solution. And it's that complex which produces, in this case, the very intense kind of blood red colour of this complex. And so we know that when we have the maximum concentration of the complex, that's going to give us the highest absorption of that particular colour. And therefore we know that we've mixed our ligand and our metal in the same ratio as they actually exist in the complex. And so we can see the sort of schematic for here, schematic of how we do it here at the bottom left. We normally take light of a certain colour, which is produced via a filter. So we take, in this case, we take our white light, our full spectrum of colour. The solution is red coloured, so we're interested in red light. We can go back to our chemistry colour wheel a couple of slides ago and see that really the opposite of red is kind of blue in terms of colour. So we'd use a blue filter, which is going to absorb essentially all of the wavelengths of light and leave just the red light that we're interested in. We want to match our light to the solution. And so then we pass our red light through our solution. And then this thing gets passed through and goes to a colorimeter. And so the colorimeter is measuring the amount of light that comes out the other end. Essentially what we're looking at here is the absorbance, so how much light hasn't come through the other end. So the absorbance and the transmittance are two different properties. The transmittance is telling you about how much is coming through. The absorption about how much essentially does not come through and has been absorbed by the sample. And what we actually kind of measure with this colorimeter is absorbance. So how much of that light that we originally put in, that red light, gets absorbed by the compound. So normally we'd have this where we have sort of two solutions, one that is just going through a sort of clear solution, so we have a sort of background to reference it against, and then the actual red light going through our particular solution. And so we measured the absorbance. And so here we have a red light going through the mixtures of this aqueous iron, 3 iron, hexaaqua iron, and our potassium thiocyanate solution. And we can see that we plot the absorbance on this graph, and at the maximum point, the point where we get this kind of plateauing of the line, but where that starts is when we have a 5 and 5 ratio of iron to thiocyanate, essentially a 1-to-1 ratio. And so it tells you that we have, for every 1 iron atoms, we have 1 thiocyanate linked. And so we know that we started with our aqueous hex-aqua ion octahedral complex, and so it'd be reasonable to assume that if we have 1 thiocyanate ligand for every 1 iron atom, that essentially the complex has had 1 ligand substitution occur. Remove one of the waters and put the thiocyanate ligand in, and so it'd be reasonable to assume that the colour of this kind of the formula for this blood red coloured complex is Fe-H2O5 SCN, 2 plus ions. So the SCN is a negative ion, 1 minus negative ion, and we have an iron 3 plus ion, so our overall complex charge is plus 2, and we have 1 thiocyanate for 1 ion. So time to have a go at some questions, all to do with the colours of transition metal ions. So if you'd like to have a go, pause the video, and the answers will be on the next slide. So the first question here was thinking about the electronic configurations really of the copper 2 plus ion, which is coloured, versus the zinc 2 plus ion, which is not coloured. Now remember I said that really one of the key things for why transition metal ions were coloured compared to lots of other main group and organic molecules was that we have this part-filled d orbitals. The key thing for the colour was that electronic transition between lower energy and higher energy d orbitals when we're in our compounds. So we have to think about our electron configurations here. Now remember that copper is one of those slightly odd electron configurations. If we're filling sort of normally with the Aufbau principle, where we fill our lowest energy orbitals first, we use Hund's rule to fill them singly rather than pairing them up straight away. We'd expect that our copper atom would have our electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Now we can sort of shortcut writing all of those down by simply putting the electron configuration of argon, that is 1s2, 2s2, 2p6, 3s2, 3p6 down in just square brackets. We write argon in square brackets and that covers all of that. But remember that actually for our copper atom, we promote one of our electrons from our 4s orbital into our d orbitals. This massively increases the exchange energy available to us. That makes a lower energy and more stable electronic configuration. And so our copper atom has our configuration of the argon 4s1, 3d10. So if it's a copper 2 plus ion, remember that we lose the 4s electrons first. So we lose the 1 from the 4s, we lose 1 from the 3d. And so our copper 2 has an electron configuration of the argon 3d9. If we do the same thing for zinc, zinc's right at the end of our d block, the zinc atom electron configuration would be argon 4s2 3d10. So then we lose our 2 4s electrons first, and that leaves our zinc 2 plus ion having the configuration of argon 3d10. And so this means then that copper has an incomplete d subshell. We have 9 electrons. We've got 1 space in our d orbitals essentially. And because colour arises from the movement of electrons between d orbitals, it's imperative that we have partly filled d orbitals. We need a sort of space to move a lower electron up to a sort of higher energy space. And so if we have this these incomplete d orbitals, then our electrons can move between these orbitals, move between the higher and lower energy levels when they split in those different shapes. And so when the electron moves up, it absorbs energy. That corresponds to particular colours and wavelengths of light, and therefore it produces coloured ions by leaving the wavelengths of light that are not absorbed, and that these are in the visible region of the electromagnetic spectrum, so we can see them as colour. It's not possible for the zinc 2 plus ion because the d subshell is complete. It has 10 electrons, and hence the electrons can't move in it. While we might be able to get our higher and lower splitting, there's no space for a lower electron to move into a higher orbital. So because the electrons can't move, we can't absorb this energy, and therefore we have colourless ions. Second question, we were given the equation of delta E equals h nu, and asked to explain what each of the terms were. So delta E is simply the change in energy between 2 energy levels. So when we saw our octahedral and our tetrahedral system, we saw that we had this splitting, the 5d orbitals splitting to either have 3 above, 2 below, or 3 below, 2 above. And so delta E is that change in energy between those 2 energy levels. H is Planck's constant, and the nu symbol, which looks like a V, stands for frequency. Remember, there's also the other form of that equation where frequency and wavelength are inversely proportional to each other, and so it can also be written as delta E is equal to hc over lambda, where c is the speed of light and lambda is our wavelength. And then part 3 essentially was to explain why transition metal compounds are coloured again, and why we don't see this for main group and organic molecules. And so it's basically everything we've been talking about in this video. The transition metal compounds are coloured because they have part-filled d orbitals. That's the really key point. And as single atoms or single ions, these transition metal atoms and ions have 5 d orbitals of all the same energy. However, when we're in a compound, the presence of other atoms, the ligands, means that some of the d orbitals will have different energies. And we've seen here that they can split, with some going up and some going down in energy. Now, in different complexes of the same element, of the same metal, these d orbitals will have slightly different energies. We say their orbital splitting will be different. The idea of that delta E value, the energy difference between the lower and the higher d orbitals, actually depends on what kind of ligands we have around. In different complexes, that delta E value is slightly different. So electrons can move between these energy levels provided they are supplied with the exact discrete energy difference between those two energy levels. We call this excitation, and they absorb that amount of energy that's equal to that difference between the levels. And so our light, our energy in the form of a photon, is absorbed, and it causes an electron to be excited to a higher energy level. A photon is just essentially a quantum of light. You can think of it as the particles of light. So light exists as this wave-particle duality. The photons are the kind of discrete packets of energy. You think of particles rather than a wave here. Now, the energy that is absorbed will be equal to a certain wavelength of light. We saw that from the equation in the question above. And so this colour is missing from the spectrum. If we take our complete spectrum of colour, our white light, essentially the wavelengths of the colours that we absorb in that compound are missing from what comes through. And so we see the remaining colours, the remaining wavelengths of light that are not absorbed. And the really key part is that transition metal ions have these part-filled d orbitals. The key thing there is that we can then have an electronic transition if they're all of the same energy, or if we have these d orbitals being empty or completely full, we can't have electronic transitions. So they have to be split, which is due to the fact that we have these d orbitals in our transition metals, and they have to be partly filled. And the other thing is that our energy gap corresponds to visible light, so we can see it as humans as colour. Now, the reason why often we don't see this in organic and main group compounds is because we don't have these partially filled d orbitals. However, there is still electronic transitions possible within other molecules that might not be transition metal based. And for organic compounds, the colour that we see in organic compounds is often due to extended conjugation. Now, conjugation is just essentially alternating single and double bonds. So if you had a double bond, single bond, sort of like you'd see in benzene, you have alternating single and double bonds. If you extend that to a much larger sort of longer sort of chain, we end up with what we call conjugation. And the effect of this conjugation is that this energy gap for an electronic transition actually gets lowered, that delta E gets lowered, and it brings it into the visible light region. But that only happens when we have this extended conjugation. So you've probably dealt with lots of organic compounds previously that have just been simply white solids or colourless liquids. The ones that do show colour tend to be much bigger organic molecules with this extended conjugation, because it brings that energy gap, that electron transition energy, into the visible light region. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on the tuition website. I offer online tuition for chemistry, so please check out those tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.